Hi everyone, how's it going? Thanks everyone for the talks so far, they've been awesome. I've really enjoyed them so far, so hopefully I won't let the slide down. So I'll just get right into it. So as by way of introduction, I'm going to sort of talk a little bit about my career, or where my career started, because it provides some of the inspiration for this generating generator stuff. So like the late phase pharma companies, does anybody work in pharma? Yeah, some people, cool. Well, it's quite an interesting technical challenge, because basically what it is they're long past the stage of checking if the drug is sort of safe for humans to consume, and they're more onto the point of checking whether it actually works. So they're testing on humans at this point, and this part of their like time is kind of like running out on whether they're going to be able to sort of make money on on this drug. They've already spent like about 7 years at this point, getting to that point, and and so now they've just got to sort of test its efficacy, which is like whether it basically works, and like from my point of view, I was this like super junior developer at this point. But basically, like what it seemed like is that they have this sort of succession. The companies that do this sort of specialize in late phase trials, and so they just have this succession of data models that they have to sort of rapidly set up, collect a bunch of data and analyze it, and then move on to the next one. And they have to sort of do it as quickly as possible. So it's not like other things where you've got this one system that you're just sort of building and like constantly building and growing the one system. You're just sort of you got a system, move on to the next one, move on to the next one. So as a consequence, all these companies sort of got together and defined this model called CDISC. That was basically like this kind of metadata model for defining the information that you would want to collect. And this was like really interesting. As I say, I was like really young developer, and it seemed it really sort of taught me the value of sort of metadata. And so like the company that I worked for, really cool company called Formedics, we would like sort of use this metadata to create or curate libraries of like study elements that these pharma companies could sort of reuse between from study to study, rather than sort of build it from scratch each time. They would they could sort of generate like entire study definitions. So rather than be tied down to a single so it was called EDC, like electronic data capture, tied down to a single EDC vendor, they would, they'd be able to make them compete against each other and lower their prices, and we helped our customers sort of like drive transformation processes. So you would have data in one format for operational purposes, but then when you wanted to compare it across studies, you'd want it in a more of a sort of reporting format. So you could use this metadata to basically to drive the processes that would transform the data from one format to another. So my objective today is to sort of show, just to take another form of metadata, which is the information schema in SQL, and show how you can, show how we at Funding Circle use that to test like a data integration pipeline. So yes, that's what it is. So Funding Circle is where I work now, and Formedics was the cool little Scottish company where I cut my teeth as a developer. Yes, that's. So who knows about the information schema? Has anybody used it before? Okay, yeah. So that's not very many. So this is a thing that is in like all SQL databases. this is like you probably can't make out any of the detail here, but like this is kind of an ER diagram of the information schema for MySQL. So it's basically just a bunch of tables that contain information about the data structures that are in your database. So you've got like a table for columns, a table for triggers, a table referential constraints. All so it's like it's all in there. All the data about your data is in the database. It's pretty meta, and it's great because this is an ANSI Standard. So this has been an ANSI Standard since SQL 92, so it's like super old tech, you can find, and so you'll find all of these tables in all the usual suspects. You've got like Oracle, Postgres, SQL Server, MySQL. It's going to be the same, set up the same in all of those different databases. But even some of the newer, sort of more exotic databases that you might find these days, Presto for kind of like data lakes, and MemSQL for, like basically distributed memory, like in-memory databases. So I was before this talk, I was like, okay, what databases actually support this thing? And these ones came up, and there was actually a few more that I didn't even include in the slide. So as I mentioned before, it's like just tables. So you can query it like any other like data in the database. You can sort of filter it with where clauses, group it. Anything that you can do with SQL, you can use to query this metadata. So it's machine readable. It's like super machine readable. So what is in the so for the purposes of this talk, what we're trying to do is generate specs. Basically, we want to generate test data, and so we're going to see what is in the information schema that will help us generate test data. So the first one is the columns. There's this so information schema.columns in MySQL. I think it's probably something slightly different in Postgres, but anyway, so we were working with MySQL, so this is what we've got. So you've got the column name, the table that the column belongs to, the data type, whether it's nullable, and then depending on the data type, you would have other things like, so if it's a string type, then you get the character maximum length. If it's a numeric type, you get the precision. Same for dates. And I think that's about it that we're going to use. So there's other stuff as well, but that's not going to be relevant in this talk. And then the relationship information. So this is information about how the tables relate to one another in the database. And you only get this if you add foreign keys to your tables. So now, I've certainly worked in places where that's not a thing. Well, I think generally like Rails apps, I've worked in Rails code bases where all the kind of the constraints and the sort of relationship constraints you do in the Rails model, and so you don't tend to want to have that in the database. But I think it's really good to have it in the database because that's really going to enforce that the invalid data doesn't get in there. So it's great to have foreign keys when you create your tables. You can add your foreign keys, and if you do, you get all this good information in the information schema about which again you get the table that the relationship sort of starts from, and then the table that it sort of points to, and the column that it points to as well. So that's all we're going to need to generate some specs. And the other thing is that this is just sort of, yeah, like information schema is kind of like an abstract idea, in my opinion. And whatever platform you're using, you'll sort of find information schemas specific to that platform. So at Funding Circle, we use like Kafka and the whole sort of Confluent sort of stack. So they've got like the schema registry. And so if you're basically, if you're writing sort of messages using Avro to Kafka, then you'll probably be familiar with the schema registry. It's just like an HTTP service that stores all of the schemas that you use to write data to your Kafka topics, and so you can like query that with HTTP. It's just like an HTTP service. You can hit it with curl or whatever. This other logo here is GraphQL. I haven't actually worked a lot with GraphQL, but I understand that there's, you sort of define schemas for your queries and your results, and you can either sort of generate that, or it's kind of like a sort of artifact that gets generated by the code that you write. But there's basically there's a valuable sort of source of information there in those schemas. And then the other one is, it used to be called Swagger, I think it's called OpenAPI now. Again, that's just this like JSON representation of metadata. And you can, so you can use this to do really useful stuff. So what we're going to do here is take the column metadata that we were looking at before, and the relationship metadata, run it through like a little clojure program, and spit out clojure-spec and Specmonstah. And so if you haven't heard of Specmonstah yet, don't worry, I'm going to explain that a little bit later, but I'm hoping that most people are familiar with clojure.spec. And so, this is basically how it works, right? So we, so we would, somewhere in, we have this project where this is kind of implemented. It's not open source yet, but I'll try and get something out of it. But basically we have like a line alias that runs sort of genspec, and it sort of just queries the information schema, runs the data, runs that metadata through the clojure program and spits out the output to this file, which we then check into the code base. And that file kind of ends up looking something like this. So because it's generated, it probably looks a little bit ugly, but we sort of don't care because it's generated. And it happened to be a little bit easier that way. So this is just a bunch of spec defs, and as you can see, there's a variety of different types here. So some of them are nullable. You've got an enumeration here for the addressable type, and a date time for the manual update thing. So these are just pretty vanilla clojure specs, and I'll show you the way that the database sort of types map to clojure specs. And then even simpler, I would say, is the sort of key sets. So for each table, you end up with a sort of set of a clojure, like a keys, a clojure.spec keys, which is just an enumeration of all of the columns in that table. So that's pretty easy. And then so here is the query to get that, fetch that data. Fairly self-explanatory. There's the only kind of thing of interest here is like we sort of swap this table list for basically the set of tables that we're interested in the database is because we weren't interested in all of them. The other cool thing, I didn't know about this until recently, but the order by. So if you just use numbers, you don't have to kind of spell out the things that you want to order by. What this means is order by table name and column name. That's just a little cool SQL trick that I learned fairly recently. And so the next two slides are going to be basically how we map database types into clojure-specs. So in MySQL, you've got like tiny int, small int, medium int, and there's just like a page in the docs that kind of shows you the limits. And this is just the Clojure sort of spec generator int in. That gives you like a spec that ranges from -128 to 127. So you can, so this will, so the generator for tiny int will generate integers in that range. And so that's all fairly self-explanatory. I think there's nothing really interesting there. Date types are a little bit more interesting. We want to generate java.sql.dates. They play a little bit more nicely with the libraries that you tend to use, like the clojure.jdbc library. If you generate like a date and put it in a parameter that you pass to a query for that library, then if it's like if it's like say a Yoda date, then I think you need to have a little bit of extra custom code. But if it's just a SQL date, then it'll just you don't need any sort of extra things in there. So that's quite nice. And so what we're doing here is we're generating an integer between 0 and 30. And then just subtracting that from the current date to get like a realistic looking date that we can use for test data. And then we're doing a similar idea for the date time here. We just 0 to 10,000, and treating that as like milliseconds since the epoch, and subtracting from the current number of milliseconds since the epoch. So that gets us our dates and date times. Decimal types are a little bit more complicated still. So this is something I kind of had sort of learned while I was doing this. But in decimal types, you've got this idea of precision and scale, and so it goes back to sort of, I do vaguely remember this from school, like the idea of like significant digits. So significant digits is the number of digits like in the number, including both sides of the decimal place, I think, and then the scale is the number after the decimal place. So the example I've got is so if you've got like the number 99, that has got a precision of 2 and a scale of 0. If you've got the number like 420.40, the precision is 5 and the scale is 2. But ultimately, for each possible precision, you can define this as a range of doubles using clojure.spec. So you're basically just going. So if your precision is 5 and the scale is 2, then your max is 999.99 and your minimum is minus 999.99. At least that's my understanding. It seemed to work. And so that's what we're doing here. We've got this like little helper, precision numeric, just takes the max and min, and then it generates a spec that generates numbers in that range. And then this is the second last one on the clojure.spec. So it's just a little string helper, string up to. So that generates random strings up to a maximum length. And so for char and varchar, it would take the maximum from the character maximum length. That's coming from the information schema. For long text, that's the limit of that is actually huge. So we just kind of cut that short to 500. Otherwise, tests would take too long to run. And then the get out clause was custom, basically like custom types. So for things like sometimes we all have database schemas where there's like a string field, but actually it's an enumeration, or like it's kind of nullable, or it's nullable, but really it should always have a value. And so sometimes like the information schema will sort of make you think that it should be, it should have some spec, but you kind of want to override that in special cases. And so this is how we do that by having a map that is keyed by the table and the column ID, and then we can just attach a custom spec in that way. And then when we actually come to sort of generate that spec file, it will sort of look up here first and override any defaults. So Specmonstah. So who's all heard of Specmonstah? Okay, quite a few. Cool. So Specmonstah builds on spec by allowing us to define relationships between the basically between the key sets that you define in spec. And so by doing that, it lets you, if you sort of hand these relationships to Specmonstah, then it will be able to sort of generate an entire graph of objects for you. So the name Specmonstah is really cool. It's funny. I don't know if anyone's familiar with Boston here, but they've got like their baseball team, the Red Sox, has got like the green monster, which is like the big green wall that you try and hit it over to do a home run. So that's the monster part, and then they have their accent. It's like Monstah. So that explains the name. But yeah, so we're going to what we want to do is take the information from the key column usage table in the information schema, and we're going to use that to generate Monstah specs. So Monstah specs look like this. So you've got like a prefix. That's just like when it generates these graphs, it gives each node in the graph like a name. So that's the prefix. The spec is just where it like generates sort of values in the graph. The relations is where you're actually saying, yep, this attribute in this table points to this other attribute in another table. And the constraints is not, that's not sort of saying that country ID is completely unique. It's just saying that it's unique within the object graph, which could be a little bit confusing if you're thinking in terms of databases. So this was kind of like this is what we're going for here. So this is an actual test in our code base that does this kind of data integration pipeline. And so what so I'll let me sort of explain. Yeah, so 5 minutes left. So yeah, so anyway, this is what we're working towards, and then I'll explain the last few parts. So this is the system that we're trying to test here. We've got 3 different databases, but they're all kind of identical, one for each region that we're operating in Europe. But they've all got identical structure, and so we want to write a test that puts data into one of the databases, or really all of them, and then it relies on Debezium, which is kind of like a data change capture tool, to take the streams from the data, writes out to Kafka, and we've got a Kafka stream that applies a few sort of transformations before sending it off to Salesforce, which is kind of aggregating it all up, and that's the tool that the users use. So we want to write this like end-to-end test, but the transformation is all sort of very like mechanical. There's not a huge amount of logic to test, but we just want to make sure that it's kind of like a sanity check to make sure it all works. We've got unit tests to test the actual logic, but we want just an overall smoke test. So there's one final bit of technology that we sort of need to do this, and it's like the test machine. So it's part of Jackdaw, like Andrea was talking about Jackdaw before, and the test machine is it's just a way to test anything where the input or output can be captured in Kafka. So basically you tell it a bunch of topics to watch in Kafka, and the test machine will just sort of sit there waiting for data to appear in those topics, and it'll load that data into the journal, which you can see there. And so the journal is just is a clojure agent. I don't know if you're familiar with it, but that's just a clojure, one of the sort of asynchronous data structures in Clojure, which basically, yes. So you've got this process that's sitting there in the background, and it's just loading data from Kafka into the journal. And then the sort of the final test command is typically like a watch that is waiting for the journal to achieve like some kind of state. You're waiting for some data to appear in the journal, and you have a predicate that returns true once that data appears, and then you get to see a snapshot of the journal at the end, and you can run all of your assertions on it. So that's the sort of core proposition of the test machine. And so what we're going to use, so building on from the data that we, building on from what we've learned about the information schema, we can sort of generate these test commands, and so what we're going to do is like build a test wrangler function, which is basically brings together all of the things that I've spoken about today, but all of this sort of stems from the data generation. That's kind of what starts off this sort of cascade. So we use the model that we've generated to generate this graph of data, and then so that generates all of these test commands. So what you see here is you've got like the inputs. So you see the inputs there. That is like a vector of the data that represents this graph of objects. And so we just iterate through that, and it's all in order. Specmonstah sort of guarantees that it's going to be in the right order, and we just insert that into MySQL. And then we also use we also use those inputs to generate the watch function, because we know, like now that we've got that data, we use that to figure out what to watch for when it's like what will tell us that it's finished, and then we just sort of put a timeout, and then we also use it in to set up the system under test. So one of the things in Kafka that you need to create all the topics in advance before you start writing to them or trying to read them from a Kafka stream. We want to truncate the tables so that we're starting from a clean slate. The connector fixture also, so that sets up a Kafka Connect job that, and so based on the inputs, it knows like how to configure that Connect job. And then the K-stream fixture is just this, that's just like what starts up the program. And then very quickly, finally, like this is what allows the kind of DSL magic that that makes it kind of look quite nice. But we're basically after applying all the test commands, the test helper uses sort of callbacks that are provided by the author to extract from the journal all of the data that the author is interested in. And so in this case, what we're basically looking for is like before and after a lot of the time, so the before representation of the data and the after, and that lets us define these like super simple predicates that are just running like assertions, and they get to see the data. They don't have to do any sort of interoperation with Kafka or anything. It's just like, just the data. And so that ends up with like a nice simple looking test that sort of wraps it all together.
Cool, thank you very much.